Okay, surface area and concentration and the rate of reaction. So again, we're keeping in mind as we do all of these things that to have a successful chemical reaction, we need two things. We need a collision between the reactants in the right combination to allow them to form the products. And we need that collision, the particles in that collision, to have enough energy to allow the reaction to proceed. In this topic, we're going to be focused on the way to increase the number of collisions. In a heterogeneous system, the way that we can increase the number of collisions is by having a greater surface area of contact between the two substances. The more contact we have between these two substances, the more opportunity for collisions we have. Imagine, for example, a reaction that you're trying to prevent, like the rusting of your car. One way you can prevent the rusting of your car is to paint it. This limits the exposure between water vapor in the air and the iron surface of your car that you don't want to rust. Again, if this is the iron surface of your car, and then we put a thin layer of paint on it, then there's no way for an H2O molecule in the air to get to the iron and have a successful collision to cause this rusting. So by limiting the surface area, we limit the rate of reaction. We limit the opportunity for collisions. Similarly, imagine starting a fire with many small pieces of wood. Or one large piece of wood. If we have these tiny sticks, these tiny pieces of kindling, then there's a lot of surface area where that wood is able to be exposed to the heat of the fire and have collisions with oxygen molecules that are high energy enough to cause the wood to combust. So the surface area provided by these small pieces of wood provides opportunities for collision. Alternatively, if we imagine a log of wood and we're trying to light it on fire, the energy from our fire can only really hit one small spot on the surface area of that wood. And while we might create a little bit of burning there, we're not getting enough surface area, we're not getting enough area where collisions could occur so that we can get this entire log to start to combust. All this wood that's existent on the inside of that log isn't being exposed to energy at all and isn't available to be collided with to provide the opportunity for a possible chemical reaction. In a homogeneous solution, we can imagine that the actual concentration of reactants is what leads to a higher rate of collision and a higher rate of reaction. Imagine that I have a dilute solution containing A and B, some things that want to chemically react with each other, and these things are naturally floating around in the solution in random ways. The best way to create more collisions would, instead of having a dilute solution, would be to have a concentrated solution. Simply by putting more of the reactants into the same area, I'm going to increase the likelihood that just through their random motions, I'm going to have natural collisions between these particles. When these collisions occur, if those colliding particles happen to have enough energy, then there's an opportunity for that chemical reaction to happen. So by having more of them, we increase the number of collisions and, as a result, the reaction rate. So in a heterogeneous system, it's about surface area. How much contact can I get between the two particles to get positive collisions that lead to reactions? In a solution, it's easier to look at just the concentration. As these particles are spread out in and around each other, the more of them that we have, naturally the more opportunity we'll have for collision and successful chemical reaction. So that's how we can use concentration or surface area to increase or decrease the rate of reaction.